Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Senpai. Welcome back, everyone. Today we're jumping into an 8th grade topic, scientific notation. Now, if you're new to my channel, I'll be putting time codes in for this video in the description box below, so you can skip ahead to whatever part of the video you think is most interesting. Always remember, if you have any question about what you see here today, put them in the comment box below. I'd love to be able to help you as much as I possibly can. If you have a question about your own homework like seen on this channel, feel free to visit me on my Facebook page at Tutor Me Senpai and tell me all about it there. When you find this video helpful, remember to leave a like. It really helps this channel get these videos to a lot of other people who may also need some help. And while you're at it, don't forget to hit the notification bell, smash the subscribe button, and share this video with a friend. Well, without further ado, let's jump straight into some scientific notation. The first thing we're going to talk about regarding scientific notation is why is it important? Why is it even used? If you've seen scientific notation before and you've never really understood it, you might be questioning, why do you even have to learn something like this? It's really puzzling and it doesn't seem like it has any real use. Well, that's actually not the case. Scientific notation is very, very useful, especially when you're dealing with super large numbers or super small numbers. So let's take this example. You have all of these planets, and I'm pretty sure you're familiar with the planets. And if I told you to look at these numbers that are associated with these planets, you will see that you have some that are bigger, some that are smaller. These are the diameters across these planets, and if I wanted you to put them in order, you can kind of do that at a glance. These numbers are not that big, although they're pretty big, they're not that big that you can't necessarily compare and then reorder them. However, scientific notation really comes in handy for much bigger numbers. So let's take Uranus and Neptune from this picture. Looking at their diameters, they seem relatively close. Uranus seems like it's just a little bit bigger, a little wider across than Neptune, but let's say I wanted you to compare their mass, for example. So the mass of these two planets, which one do you think will be bigger? Uranus because it's a little bit wider, or Neptune? Well, let's take a look at their mass, and I want you to, in 2 seconds, tell me which one's bigger. If you can tell me in 2 seconds which one is bigger, you win this one. But if you can't, you see why we use scientific notation. These are the masses of Uranus and Neptune. And remember, you only have 2 seconds. Which one is bigger? Now, if you're trying to go off of my handwriting and where the zeros fell off, you might have gotten a little confused because my handwriting is not uniform. I didn't write all my zeros the same. I didn't write all my numbers the same size. So it's kind of hard to compare. And if you guessed it, well, good job. Neptune is actually bigger. But guessing is not going to work, especially in this scientific field. You have to know for a fact which one is bigger, especially when you have numbers right in front of you. You can't do guesswork. So these are really large numbers, and it can be easily confused miscounting how many zeros are here. They're so close that any one could be easily mistaken for being bigger by just dropping off 1 zero. So scientific notation really helps out when you have these big numbers. Compare them. I'll show you how in a little bit. But big numbers, like I said, aren't the only ones that it helps with. It also helps with really super small numbers. Let's take this, for example. Here we have the mass of a proton and the mass of an electron. Now, protons and electrons and neutrons are very small components of an atom. However, looking at these, you might be able to see which one is a little bit bigger because just how I wrote this. But what if I ask you at a glance to tell me how many zeros are before the first non-zero component of these masses? So how many zeros before the 1 for a proton and how many zeros before the 9 in an electron? Could you easily, quickly, within 2 seconds, tell me both of those? Probably not. Well, that is also where scientific notation really comes in handy. At a glance, it will show you just how many zeros are incorporated inside your number to see how big or how small it really is. So we just talked about why it's important and how it can be really useful for classifying big and small numbers, but what is the form that allows us to take advantage of this? Well, the form for scientific notation is very easy. You're going to have a number times 10 to some exponent. So I'm just going to say this is another number here. Some exponent. So there's 3 components. A number times 10 to some exponent. That is the form of scientific notation. So let's take an easy number. Easy number. So let's say 5. 5 is a number that we don't have to use scientific notation for, but it can be written in scientific notation. We typically write our numbers in like standard notation, decimal notation, but we can write this in scientific notation if we wanted to. So we would take 5, times it by 10. Now, when we times it by 10, that would change it, right? Because we know that if we just did this math here, this would be 50. And we don't want that. We want 5. We don't want to change how this looks. So we're not going to actually just multiply by 10. We need that exponent part. What is this exponent going to have to be in order to not change our number? Well, that is going to be 0, right? Because anything to the 0 power is going to be 1. If you need more practice with exponents, I made a video talking about some basic introductory exponents. I'll link right above here. So 10 to the 0 is really just 1. So we're not multiplying anything that's going to change our number. This is just another way of writing 5 times 1. But you see we have a number times 10 to some exponent. This is another way of writing 5 in scientific notation. But it's not that impressive. Let's take something else. Let's take something just a little bit bigger and see if we can write that in scientific notation. Let's say you have a slightly bigger number, 365. This is something that we can write in scientific notation as well. But unlike before, we just had the 5, we're not going to do 365 times 10 to the 0. That's not scientific notation. And you might be asking why we did the same thing for 5. Well, that's because scientific notation, although we have a number here, it has a very specific form for that number here. There's only supposed to be one digit before the decimal. Now, decimals, if they're not written, they're typically understood to be after the last digit of your number. So this is really 365 with a decimal point after it. This is not scientific notation because we need only one digit before the decimal, and here we have 3 digits before the decimal. This is not scientific notation. However, we can make it into scientific notation by having the decimal here. But that changes our number. We're no longer 365, we're 3.65. So how do we get back? So in order to get from 365 to 3.65 without changing the value of our number, we're going to have to multiply this by 10 to the second power. And I'll explain why in just a minute. If you already see it, good job to you. But if you don't worry. I'll explain this in more detail in the next part. But what I really want you to see is the form of your scientific notation. You need to only have one digit prior to the decimal, and it doesn't really matter how many digits after. The same thing can be said for small digits. This, if you just were to do 10 to the 0 here, this is also not scientific notation. But you might be asking, hey, we have one digit before the decimal, and you said we have any number of digits after. Why is this not scientific notation when the other two were? That's because although I said one digit before the decimal, it has to be a non-zero digit before the decimal if it's truly going to be scientific notation. Remember, your 5 in that situation was 5 times 10 to the 0, but remember, your decimal is understood to be after your last digit of your number. 5 is only one digit, so after that is your decimal, and it's a non-zero digit. So this is in scientific notation. However, this up here is not in scientific notation because that is not a non-zero digit. So in order to write this in scientific notation, we need to write it as 7.8 times 10. In order to not change the value of this, this has to be to the negative third power. This is going to assure us that we have the same exact value and we only have one non-zero digit before the decimal. This is scientific notation form. Now, if you're not familiar with negative exponents, I also have a video on negative exponents you can check out. I'll link it up top here as well. Now that we have the form down pat, how do we convert a number from standard notation to scientific notation? We know that it has to have one digit that is not 0 before the decimal, and it has to be multiplied by 10 to some exponent, but how do we do that? Let's say we have this number here, 12,345, and we want to write this in scientific notation. Well, the first thing I want you to do is write this with a times 10 to the 0, because we can write any number in this form because 10 to the 0 is just 1. It doesn't change the value, but this is going to be really important to kind of see how we're going to be doing our stuff here. Our number is going to be times 10 to the 0 power. Without doing anything, that is what we're going to start with. And we're just going to play around with this exponent here until we get something in scientific notation. We just said that the decimal, if it's not written, is understood to be after the last digit of your number. So I'm going to put the decimal here. But what happens if I were to put the decimal here? I'm going to move it over to the left, at least one spot here. I'm going to rewrite this. So now it's going to be 12, 3, 4, decimal 5, and times 10. But is it still times 10 to the 0? No, actually, because we moved it over 1, in order to get back to what we want, we need to put a 1 here. We moved it over 1 space to the left, so we're going to have a 1 here. Let's do this again. If we want to move it over 1 more space, because this is not scientific notation. So it's going to be 12, 3, decimal 4, 5 times 10, and we have to go 2 spaces because we've moved it over 2 spaces from the first point. 2 spaces, 2 is our exponent here. You might see a pattern. We're going to do this, and this time we're going to move it over the last 2 spaces because we want this to be in scientific notation. 1 non-zero digit before the decimal. So that's 1.2345 times 10. Now it's not going to be 3 because we actually did 2 more spaces. So how many spaces have we moved from the beginning? We've moved 1, 2, 3, 4. So this is going to be 10 to the 4th power. That's all you have to do in order to get your scientific notation. You start here, and if you're going to the left, you're going to be adding numbers to your exponent. You start at 0, and however many digits you move to the left, that's what your new exponent is going to be. But how about the other way? What about small numbers? This was a pretty big number, but how about small numbers? Small numbers are going to start the same way. I want you to do your times 10 to the 0, especially when you're just learning this. Start here, and we're going to try to get 1 non-zero digit before the decimal. We don't have that yet. So we got to move it 1 space this way. And when you move it 1 space this way, we get now, we're going to still put a 0 here. And I'm not going to keep adding multiple zeros before the decimal because we don't need all those zeros. So I'm just going to shave it down to just 1 0 before the decimal. And then we're going to just kind of keep everything after the decimal as it is. So we have 2 zeros, 8, 5, 7 times 10. And it's not going to be 1 this time because we're going this way. Previously, we were going to the left. Now we're going to the right. So this is going to be a negative 1. Whenever you move it to the right, it gets negative. So we're going to do it again. Move 1 more space to the right. And we're going to put 0.0 is only 1 0 after the decimal this time, right? Before you get to your first non-zero digit. And this is times 10 to the negative 2. You see a pattern here, right? We're still changing our exponent by 1, but this time instead of increasing it by 1, we're decreasing it by 1. So we're going to do this again. We need to move it over 2 spaces this time. And in order to do that, we're going to have to write our 8.57 times 10. Is it to the negative 3? No, we did it negative 4 because we went 1 space, 2 space, 3, 4 spaces, so we have a negative 4 here. So whenever you go to the right, your exponent gets smaller. But from our previous example, whenever you go to the left, your exponent was getting bigger. Let's put a rule out for that. Initially, we always want to start at 10 to the 0. And if we're going to move our decimal over to the left, that makes our exponent increase. So we're going to go bigger. It's going to have a bigger number in your exponent. However, we move our decimal to the right, we're going to make the exponent decrease. So if we start at 0, we're going to get more negative. So let's practice this with our earlier pictures of our planets, and let's see if we can, at a glance, check which one was bigger for Neptune versus Uranus as far as their mass is concerned. So here we have Uranus and Neptune's mass again. And we're going to use our steps. We're going to start with 10 to the 0. So you see I wrote 10 to the 0 for Uranus and 10 to the 0 here. We're not changing the mass any. We're going to start here, and then we're going to either move our decimal to the left or right to try to get scientific notation, but depending on where we move it, we're going to increase or decrease our exponent from 0. So let's start with Uranus. And remember, the decimal is going to be right at the end. So in order to write this in scientific notation, we need to keep 1 non-zero digit. How many digits do we have here? Let's first count those, and let's take off 1 for the last digit because that last digit is a non-zero one. So we're not going to count that one, but in order to move it to the left and only reserve this, we need to count up all the other digits we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So we have 25 digits outside of our first one. So we're going to actually put this right here at 8.68, and we moved it over to the left, so our exponent should be increasing by the number of spaces we moved over. So it's going to be 25. This is going to be the mass of Uranus in scientific notation. Let's do the same thing for Neptune. The decimal is at the end, and we're going to be moving it to the left to write this in scientific notation, so we're going to increase our exponent. So let's count up everything but that first digit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So this is going to be 1.02, and you don't need to write all the other zeros. You see I kind of cut off the zeros up here. They're not important after the decimal. As long as you have your non-zero digits displayed, unless you want to round it as well, but as long as you have your non-zero digits displayed, you're pretty much good. And we moved over 26 places, so it's going to be a positive, because we're increasing the exponent, 26. You can easily see that this is going to be times 10 to the 26, times 10 to the 25th. In less than 2 seconds, you can definitely say Neptune with confidence has much more mass than Uranus. Although it looked like Uranus, if you could look at our picture from before, had a little bit bigger diameter. Let's bring back the mass of the protons and electrons as well, and let's work this again to see how we do things for the right. So we have the mass of the proton and electron again. And we said we can probably see which one was bigger between the two, but if I wanted you to at a glance tell me how many zeros each one had, that was going to be a little bit more difficult. But let's write this in scientific notation and see if that helps us a little bit more. Remember, our scientific notation form needs one non-zero digit before the decimal. We have a lot. We're going to start with proton. We have a lot of zeros here. So we need to move them over to the right in order to get this one here before the decimal. So let's count up all the zeros before this non-zero digit here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. We have 26 zeros. But if we only move it over 26, we're going to be left with 0.16. We don't want that. Remember, we want a non-zero digit before the decimal. So we have to move it over one more spot. So we're going to move it over 27 spots to give us our 1.6726219 times 10 to the 27. But we know how many zeros this has because we are going to subtract 1 from our exponent, and that's how many zeros are before that non-zero digit. So you see how this tells you just at a glance. How about this one? Before our non-zero digit, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. We have 30 zeros, but we're going to write this as 9.1093835 times 10 to the 31. Because we need to move it over one more space to get the 9 as the non-zero digit before the decimal. But we know that since we moved over one space to get that 9, we have 30 zeros before the 9, but after our decimal. We can look just at a glance. Yeah, you can see this one is a little bit bigger, right? However, you can also very easily see how big. What is the order of magnitude bigger? We have so many more zeros in this electron mass before our first non-zero digit in the decimal. Scientific notation makes that easy at a glance. So if you're working with big numbers, you might opt to work with scientific notation so you can easily see and use them and categorize them, classify them, whatever you need to do without having to spend so much time getting tongue twisted with your eyes looking at all of these zeros. We've talked about a lot of different things so far, from why it's important, how it works, what the form is, but once you get in scientific notation, is it there to stay? Can we get things out of scientific notation back to our standard form? Yes, and very easily. We're just going to reverse what we did. So instead of starting with 10 to the 0, we're going to start with whatever our exponent is, and everything else holds true. So if we're trying to convert back, instead of starting with 10 to the 0, start with what your power of 10 is. And then you're going to do the same exact stuff. If you're moving to the left, well, what happens to the left? We already talked about that. Your exponent gets bigger. Exponent increases. Doesn't change. If you're moving to the right, exponent decreases. So the only thing you're starting with that's different is your power of 10. Instead of starting with 10 to the 0, you're starting with the power given, but you're trying to get back to 10 to the 0. So that's the next part. Those steps are pretty similar, but the end result is get back to 10 to the 0. That's what you want to get. Your goal is to get back to 10 to the 0. And if you can do that, you're taking it from scientific notation back to a standard form. So let's try out a quick example and you can see what I'm talking about here. So we have these two examples here, 5.635 times 10 to the third and 7.893 times 10 to the negative 9. The end goal is this last step here. Get back to 10 to the 0. We want to get this back to 10 to the 0 and back to 10 to the 0. Then we know we're in standard form again. However, we're going to start with the power that's given to us. And we're going to move to the left or the right in order to increase or decrease to get back to this 10 to the 0. This is 3. That's greater than 0. So if we're going to get back to 10 to the 0, we need to decrease. So we're going to move it over to the right. So you see, we're going to move it this way. So this becomes, if we move it over 3 spaces to get it back to 10 to the 0, 5,635. That's it. We moved it over to the right in order to get back to 10 to the 0. We're going to do the same thing here. We want to get back to 10 to the 0, but this is negative 9. So we need to increase this. This is too negative, so we need to move it over to the left. But there's no zeros here. There's no digits. That's perfectly fine. Move it over all those spaces, and then we're going to fill those remaining spaces with no numbers with zeros. So we're going to move it over, and we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9. We need to move it over 9 spaces, and remember that 9th space is going to be this 7. So we have that, but we don't have any of these other 8. So we're going to fill those in with zeros. And then we put our decimal, and you can put a 0 up front because, hey, why not? It doesn't hurt. But you see, we moved it over 9 spaces, this time to the left. So we increase our exponent, so now we are back to 10 to the 0. And just to check, we start with 7.893. We have 7, 1, 2, 3, 4, 5, 6, 7, 8, 9. We start from after the 7 and we moved it over to the left 9 spaces. Now we've gotten it back into our standard form, and we don't even need to write this. This is only to help us understand what we're doing. When you're more familiar with this, then you can drop it off. But I really recommend you start using this to at least familiarize yourself with the steps of changing it to scientific notation and converting it back from scientific notation. It's the same exact steps, you're just kind of working in reverse. So we talked about a lot in this video already, and this video is getting a little bit long, but I didn't want you to leave this video without understanding that magic is not happening. We're not just saying this works for the sake of making it work. There's actual math that happens behind the scenes for this, believe it or not, and it makes perfect sense. So I'm going to give you some really easy examples to show you what's actually happening, and then you can kind of expand upon that to see the bigger pictures. So let's say we have this number here, 5,621, and we want to write that in scientific notation. Well, we said that writing this in scientific notation would give us 5.621 times 10 to the third power. But why does that work? Why can't we just move it over 3 decimal places and make this work and just throw a times 10 to some third power here? Why does this work? Well, because we're trying to preserve the value, we don't want to change anything. So this has to equal the same thing. So in order to do that, we have to multiply this by tens in order to get the same value here. So this times 10 to the third is really just saying we're doing 5.621 times 10 times 10 times 10. Or we can say times 1,000. And we know when we multiply by tens, we're going to be shifting decimals over. So that's all we're trying to do here. But instead of writing out all of these tens or writing out this massive number here, we're using exponents as a shorthand. So it's not like magic happening. It's just shorthand for all the little math that's repeated. So we don't want to keep writing all this out. So we just shorthand it to times 10 to the third. Imagine writing out 10 to the 31st this way, or writing out whatever this number is with all of its zeros. That is a massive number and no one wants to write all that. So we shorthand it to times 10 to the 31st, but all we're really doing is multiplying it by 10 and 10 and 10 over and over and over again in order to move the decimal place. We're going to increase the magnitude to get it back to what we need it to be, so we're not changing the value here. That's why it works. But the same thing is true when we're doing negative exponents, except instead of multiplying 10, we're dividing 10. Let's see how it works. In order to get this in scientific notation, we said this is going to be 7.25 times 10, and we move it over 4 spaces, times 10 to the negative 4 here. Whenever you go to the right, your exponent decreases. But why? That's because we're dividing. If we go from this number and try to get back to this number, we have to divide by tens. We don't want to change the value because 7.25 is very different from 0.000725. So to get it back to here, we have to divide by tens over and over and over again. And every time you divide by 10, you move the decimal back over to its original spot. So that's why we do this. But instead of saying times 1 over 10 times 1 over 10, and then keep writing this out, because this can get pretty cumbersome, especially when you have massive numbers. Or on the same note, instead of doing times something like this, you don't want to do that. This can get very big, and we don't want to do that. So we use notation that we're familiar with, exponents. And we know negative exponents, this right here is a negative exponent. This means 1 over 10 to the fourth. So we're going to pretty much take the reciprocal and make it negative, and that's how we get our negative exponent, hence why we have 10 to the negative 4 here. All that we're doing is dividing by 10 over and over and over again. Our negative exponent means we're dividing by 10. Our positive exponent means we're multiplying by 10. That is the secret. That's the magic behind it all. It works because it's math. It's not anything special besides repeated multiplication of tens or repeated divisions of tens. Now, I know that video was a really intense one, really long one, and if you were able to stick with me through the whole thing, thank you so much. I really hope that you understand that scientific notation can be a wonderful thing, especially when you're dealing with really, really big numbers or really, really small numbers. We don't really want to use the full notation because there's a lot of writing and very easy to make mistakes if you miss one digit. So scientific notation is a magical thing at times, but it really isn't magical because of all this simple math behind the scenes. However, if anything confused you in this video, anything at all, remember you can put them in the comment box below. I'd love to be to help you as much as I can. If you found this video helpful, remember to leave a like. It really helps get these videos out to more and more people who could potentially use the help. And if you haven't done so already, remember to hit the notification bell, smash the subscribe button, and share this video with a friend. Well, that's all the time I have for today. I'm really hoping this helped with your homework, and I'm looking forward to seeing you again next week. I'm Courtney, and this has been another session of Tutor Me Sempai.